Hi, my name is Vivian Ciaramitaro, and I think I'm the last person in the Early Minds Lab speaking to you guys today. So a lot of the studies that I do have to do with mechanisms of sensory processing and attention. And so I'm really interested in how our different senses often interact in ways that we're not even really aware of. So even though you're not like trained as a lip reader, if you're in a really noisy environment, you might look to your friend's lips to figure out, to better hear what they're saying. Right. And so there are a lot of ways in which our different senses interact in ways that we're not even consciously aware of. So a lot of the things that I study in my lab have to do with visual and auditory processing. More recently, we've also added studies of sense like touch processing. And we use a number of different methods such as psychophysics, eye tracking, and non-invasive brain imaging. So I'm kind of just going to give you a flavor of some of the things we've done. And again, like I'm excited to talk to you guys later. And if you have any questions, you should always reach out. And just to highlight, like none of this work is possible without the help of grad students. So some of the work I'll be talking about in the next slide was done by my former PhD student, Arinda Marina, who's now doing a PhD in France. And Shibo Kao just wrapped up his PhD and is currently looking for a postdoc. And Mahan just started. You might see him around later today. But so you can imagine, let's say in this simple example, which I kind of try to think about as like low level perception, right? The question here was, are you better at detecting an auditory stimulus, right? Telling if it's on the right or the left. And this was just an amplitude modulated white noise. So it's a sound that's kind of warbling at a particular frequency. Does it matter if there's a concurrent visual stimulus, right? So you can imagine the whole screen in front of you is changing in luminance at a particular frequency, but it doesn't provide any spatial information, right? So if it doesn't matter, right, that this is just irrelevant visual information, then all of these curves should kind of line up, but clearly they don't. So what happens is if the way that the sound is changing over time is synchronized with the way that the visual stimulus is changing over time, you actually do better, and you do worse if the two things are out of sync. Right, so this is something that we studied in adults, and we do complementary studies even in infants, right? And then kind of the high level type of perception that we study in my lab and that we're really interested in is emotional processing, right? So you could ask questions about how your ability to perceive the emotion in a face, if you're presented right with this visual stimulus, doesn't matter if the concurrent emotional information you get from a voice matches or doesn't match, right, the visual information in the face. And just within the visual domain, there are all of these really interesting implicit biases that we have, right, that we're not even aware of. And here what we did is we studied this implicit bias that's known as the angry male, happy female bias, right? So if you're presented with a face that is on average perceived as neutral, if it is like a stereotypical, more masculine face, like right with higher contrast eyebrows or facial hair, more angular types of features than the stereotypical, more feminine face, you're going to be biased to perceive this male face as angry and a female face as happy, relatively speaking. And so we looked across development from like individuals 6 years of age to like 60, looking at how these biases were changing over the course of development. Because you might imagine, like, are you socialized into some of these biases? Are they just something that's intrinsic to perception because of these like stereotypical features that are different between male and female faces? But we're really interested in a lot of different aspects of emotional processing. We've done some studies in collaboration with Dr. Hunter looking at the effects of stress by quantifying salivary cortisol. And we collaborated with a clinical psychology faculty member in our department who studies social anxiety, because in social anxiety, people have been shown to have kind of negative perceptual biases in how they evaluate faces. That someone who's not as socially anxious, like they wouldn't see this kind of neutral face as more threatening and angry. Right? So there are a lot of really interesting questions, and you can use just basic perceptual types of measures to look at the strength of adaptation. And we found that if you're socially anxious, you're just not habituating or adapting to that kind of angry information, and it means that you retain your sensitivity to seeing things as negative. right? And just to kind of give you a flavor for some of the things that we do that I guess what I would say is more like not low level flashes and tones or high level emotions, but kind of somewhere in the middle are sort of these cross-modal correspondences where we naturally associate features between our senses, but even really abstract features, right? So if you ask people across different cultures at different stages of development, speaking different languages, which of these two shapes is kiki, right? So this is kind of just a nonsense sound, and these are abstract shapes. But on average, most people would say that this spiky shape is kiki, right? So maybe some of you have heard of this Bubakiki effect. There was an article in the New York Times a few years ago. So we're really interested, like here, this is an example between audition and vision, but people have found examples between audition and like taste or touch or all these different types of senses. And we've looked at some of the underlying neural correlates because we're also really interested in the effects of attention. And just like a really quick overview, we're using frequency tagging here. So I can present a stimulus out there in the world that's modulating, let's say, in luminance at a given frequency. So becoming visible and invisible, visible and invisible. Here, this was at 5.45 hertz. So then areas in the brain that are responsive to that information will be entrained at the same frequencies. So I've kind of tagged the brain and I can quantify how much signal is in the brain in response to this particular stimulus. And then you can look to, at different effects, right? So here I'm looking in visual areas for this basic shape. And I can try to understand, like, if I'm measuring the neural response to this basic shape, which I'm just showing here by this red bracket, it doesn't matter if you're paying attention to the shape, if you're not paying attention to the shape, doesn't matter if the concurrent sound that's happening randomly, that's not frequency tagged, if it matches the features of the shape or it doesn't. And what you can see here is that there's a basic effect of spatial attention. So the responses in the brain are much stronger if you're paying attention to the shape than if you're, right? So you're paying attention to the shape and detecting if the border gets thicker, or you might be paying attention at central fixation to detect a color change, right? So with attention versus without, I see a much stronger response in the brain, which is just an effect of spatial attention. And then there's also a weaker, but a weaker tendency for the overall effects when you're always paying attention to the shape to be stronger if the sound presented at the same time matches versus doesn't. So there are a lot of different types of methods that you can use to get at some of these underlying mechanisms involved in cross-modal correspondences and thinking about how features across our senses interact for even these really kind of abstract types of stimuli. So I'm going to stop there, but yeah, I'm happy to talk to you guys later, and feel free to reach out if you have any questions. Enjoy the rest of your day.